Hi, everybody. So my name is Michael Paquier, and as written on the slide you can see here, I'm currently working for AWS, doing PostgreSQL stuff. Today's presentation is about a concept I have invented for the PostgreSQL core engine, based on my own experience on the matter and 14 to 15 years of frustration working on PostgreSQL itself. So I hope that this presentation is going to be helpful for you. It's about a development toolkit made by one developer, me, plus a few more people who have been able to be smarter than me to make things a little bit better than what I was thinking about initially. And it's really for developers. Like if you do development for the PostgreSQL core code, if you have an extension that relies on the PostgreSQL backend, you can reuse what's been added in the PostgreSQL core engine for what you are doing. So I hope that this presentation is giving you some insights and about what you can do, what you cannot do, and well, let's hear about that. So a few words about myself. As it may sound, yes, I am French. So I have a certain amount of accent when I speak English. And I'm also based in Tokyo. So yeah, if you want to talk in Japanese, I think I've done it once in Japanese. And I've been working at AWS since 2022. I have been a PostgreSQL contributor involved in the project since 2009, involved first on one of the, I would say perhaps first shared nothing projects based on PostgreSQL, which was PostgreSQL that most people likely do not know about. And since then, I've been involved in the PostgreSQL project in terms of patch author, reviews, and the community has accepted me as a committer of the project since 2018. So I've been working on that with the mindset that Robert has described yesterday in his talk. Not, I would say, as a king, but somebody where the sky is just waiting for me to fall each time I commit some code. So I've been doing that for 7 years, helping on many aspects, seeing people's patches and trying to do stuff like what I'm explaining to you today. Today's agenda, I wanted to show you a little bit the concept of the whole thing, the idea, why I've done that, a few things about the core code itself, what we have currently in the code tree, and how you can use it for yourself, how you can extend it for your own needs, and some examples we have in the tree. Today's presentation is nothing about hand-waving. All the contents on this talk are already committed into the PostgreSQL core code. We could do a few more things better. We can always do better. But that's really stuff that exists in the code, and you could just do it by yourself if you want, if you do some kind of hacking. So about the concept in itself, any talk should have a quote about when you present something, and I've been lucky enough to find a quote from last month from somebody on the public mailing list. Noah, if you're here, you deserve the credit on this one. So it's really about the injection points. It's not the first sentence, it's the second one. One hasn't fully tested PostgreSQL until one builds with injection points. I saw that and say, I need to use that in my talk, so I've just included it. But Noah deserves the credit. He deserves also a lot of the credit for things that have been improved, because I've just developed an egg, but people have been able to build on top of that. So it's really about testing. It's really about doing more things in the PostgreSQL backend. And why is that? It's because PostgreSQL makes testing very hard because of its design and infrastructure. It's a multi-process infrastructure. People talk about threading. We would still have the same problem. And it's really a matter where it's not really possible to synchronize precisely actions that happen in the backend. By action, I mean you want to be able to do something, a custom action, at one given line of the core code, depending on one command. And you want to be able to synchronize that across more than one single process. You want to be able to do that across the checkpointer, the background writer. You want to be able to do stuff in some extended way. You can do a few things, and these are based on some examples and things I've been doing when implementing some tests for the PostgreSQL core engine itself when working on bug fixes, but these are always limited. And sometimes I want to be able to do things automatically. And in my experience, I've also been doing a lot of bug fixing by using, for example, GDB across 1 or 2 different processes, doing it manually, doing that across stable branches, because also I'm a committer, so I need to check individually everything, make sure that it actually works the way it's intended to work. But point is that this doesn't scale. For example, if you have 1 fix across 7 active stable branches that need to be fixed, say an OpenSSL fix where we need to support 4 to 5 versions of OpenSSL, it makes kind of 20 to 30 scenarios you need to fix, to work on. And imagine that, for example, if you use GDB, you need to multiply that by 20 times. I want to be able to automate that. I want people to work efficient code and be able to work on stuff that matters for them. So you can use tricks. For example, there is one that I used in the past where you could be able to use log PG data to block authentication attempts, because like it's a short story. 2 years ago, we had a bug related to a backend trying to connect in the backend, and if at the same time you had a drop database happening within a very tiny window, it was possible to cause AutoVacuum to remain stuck forever because of dangling PG statistic entries. So we were thinking about, let's add a test about that, but even if we tried to do that, the test was not reliable. And that kind of what triggered what's in this presentation. I mean, it's not only that, it was much more than that. You can also use hooks. You can use test modules that we have in the PostgreSQL core code for a little bit of time. These are limited by APIs, direct APIs calls. Hooks also are limited by what you can access to in terms of structures, what hooks get passed to, for example, the utility hook, elog hook. I'm pretty sure that some of you develop extensions that do testing based on hooks, for example, loading that and track those tests. But at the end, it's always limiting what you can actually do, the amount of interaction you can have with a given stack or anything. So what I want to do this stuff, I want to be able to run, like in 2 lines, some custom code at a very precise location. I want this code to be flexible. It's something that I wanted to be able to work with it in the core code, in the extension code, and I want to be able to backpatch any test I have. So this really needs to be something that I can rely on as a maintainer of the project itself. I wanted it to be customizable and extensible, such as people would be able to build on top of what has been committed. And so I've been really trying to use a minimalistic approach, like what I've seen across many companies and many products, actually, because like if you have a large customer base and product requirements, you see that people use those kind of methods, like for advanced testing, for example, for race conditions, and people just replicate the same thing across many products a lot. I've seen that some of those implementations use, for example, their own languages on top of that, but all of them rely on interactions with the backend. I wanted this stuff also to be cheap to use. The PostgreSQL tests need to be fast and reliable while having a low maintenance, because low maintenance means that I can focus stuff on other things and I do not have to spend my time on all that. So in terms of test designs, what I've seen working on bug fixes for PostgreSQL is that I wanted for quite a bit be able to reproduce easily race conditions. False states in the backends, for example, errors, fatal, panics for the backend to crash. Also, cross-process interactions. I wanted to be able to take actions across multiple processes by making them wait and be able to wake them up at the timing I wanted. One issue with is that I also wanted to be able to know if a backend was actually waiting. If you want to be able to achieve that, that comes to have a look at PGStat activity, for example, things like wait events. So I wanted to be able to monitor that. But there is a little bit more than that. For example, say you have a variable your stack. You want to be able to do some stack manipulation of some variable you are calling into. You want that, of course, to be cheap, fast, and to have a very high reproducibility rate, such as the test you're actually running is actually, you want to make sure that it's actually checking what it's designed to check. I want to be able, in some cases, some information. I'm not sure if a lot of people do that, but sometimes I do debugging, and I like using a lot of e-log notice logs, check for patterns in the logs when I'm investigating some issues. And at the end, it comes that if I have some tests, I want to be able to show, in some cases, notice messages that these actually match with some cases, depending on what I've been trying to achieve. So those are kind of the main things I've seen as useful most of the time when it came to working on Postgres. There have been quite a few proposals on the matter across time. What I've never liked about any of them is the amount of code and the footprint these have introduced. But all of them were about the same concept. They wanted to be able to force a state in the backend to happen in a control matter. So there has been one proposal in 2020 called Better Infra for Concurrency, which I think was proposed by Alexander Korotkov, which was really about being able to do wait and waits, if I recall correctly. We have also forks of upstream that like doing things like that. There has been another proposal called ProPoint by Craig Ringer, who was part of Second Quadrant, now EDB. Peter is there. Craig is still is working for EDB. Okay. But yeah, so some of what Craig has actually proposed back is the set of ideas. I mean, I got some inspiration from the work that he has actually done. So Craig also deserves some credit when it comes to that. Greenplum, which is also open source. Now I think it's kind of a fork called Cloudberry DB. I think, sorry if the name is not right, has a concept like that, where they actually wanted to be able to do advanced testing. If you look at the code, they have a high footprint in the postmaster about the states they want to store, and they were limited by the fact that you could not plug that into your own extensions. And another matter is that I've seen quite a few products with similar requirements. So it's perhaps an XKCD, you know the guys, the XKCD commits. If you want to invert a new standard, you just need to override the existing standards. This is not a standard, but I've just taken the step of inventing something that I hope everybody would be able to use, perhaps in some kind of standard way in the PostgreSQL community. But it's kind of an overwrite of everything that's been proposed to the project for the last few years. So what do we have in the core code itself? This uses switches that are disabled by default, and you can enable them using enable injection points for configure or Meson. This is a testing framework, so you should use them for beta builds, testing builds. Do not use that in production. If you use that in production, well, it works, but that's really up to you. It's your responsibility to do that. I do not think that any of the packages enable those switches in the builds for the RPMs and such. But we enable them in the CI, and we have also testing for that in the build farm. You can see on the upper right, I mean, it would be your right, and it's my left, of the slide, there is a small icon. It's the icon referring to the build farm animals that enable injection points. I didn't know it was actually something, but I've noticed the icon like 2 weeks ago. So that's, I think, something that perhaps Andrew Dunstan has added in the build farm client. I've noticed that. So all the build farm numbers with this symbol attached to it means that they're actually using injection points in their test. The CI runs them all the time. So we have a pretty good coverage about what we actually want to do. In terms of sources, it's really 2 files you can rely on with a few APIs in them. It's injection.point.c, injection.point.h. Everything is hidden behind a set of C flags, which is called, I think, use injection point. In terms of implementation, its initialization relies on a shared memory state, which is a simple array storing a set of information about a point name, a library name, a function name that we load. We have also a concept called a private area that you can use to register some information when you define a point. But I'm going through that a little bit later. We have an idea also about we maintain local cache in each backend, such as you do not need to load points repeatedly. So it's a process level cache. We have some documentation that gives a short introduction about what you can do. But here is more interesting stuff, which is the actual code in itself and what happens in the core code of PostgreSQL itself. So we have behind the C flags, if you enable the switch, a simple macro called injection point where you can define a name and what's called also an argument. The argument is something which is very new as of really very, very new as of last Saturday, actually. I'm coming back to that in a few slides, but the idea is that you can really, it's quite simple. You can do something which is called attaching a point, which is I want for a location that defines this macro to be able to load for this given point name a function in a certain library. And I also want to be able to attach some data that's defined when the point is attached. So a point attached means that it will be run then consecutively if you call this injection point run thing. Injection point run is simply a function that we call when the macro is defined in the core code. So basically what you would do when you use injection points is that you need to use, normally you would use most of the time this one line macro in the location where you want to call a callback, and the callback will be run depending what you attached previously. So it's really about attaching a callback as one step, and the second step is to make sure that the callback is getting called at the location you want to. If you want to get an idea about where injection points are being called, you could, for example, do a git grep for this macro injection point, and you would get an idea of where we actually define those points. And if you look at the point names, you would be able to see which area of the codes, what kind of tests are related to them, what kind of callback we have. So it's really a matter of using a git grep. The concept is really attaching a callback to somewhere and be able to run it once you enable that. So there is something to be aware of, which is critical sections. A critical section in PostgreSQL as a matter of project policy cannot do any kind of memory allocation in it. The concept of loading a callback for injection points relies on one single function called internal load library in dfmgr.c. So what happens is that this does internally an allocation because you want to be able to build the path of the library from where the callback is going to be loaded. So if you do have some code that does a start critical section, you have an injection point, and then you end your critical section. Well, this is not going to work by design if you rely, because the internal load library is going to panic on that because of the memory allocation. So doing that is a bad idea, which is also why we also have the cache, because we want to be able to load the point before actually running it. So we have been working around that by using what we call cached points. The original implementation of injection points did not include that, but Heikki Linnakangas came in because he actually wanted to be able to do so. So we've come up with, instead of redesigning the internal load function API, the concept where it is possible to load a point previously without running it outside the critical section, and then you can run a point which is cached inside the backend level cache in itself. So it's a two-step process to work around the limitation caused by the limitation inside this internal load function where we do the memory allocation. So you can still use them in critical section, just make sure that you load them and just run a point which is actually already cached by the previous load. So one of the things you can also do is stack manipulation of the states. So you have a callback you want to run, and that's actually the concept that's been added last Saturday by a set of 3 commits I have done, because based on Andres has not mentioned that during his talk, but the asynchronous I/O code is doing some testing based on injection points, for example, for short reads and error states, if I recall correctly. The code was passing arguments to the callbacks, and we did not have, before that, the possibility to give at runtime some variables that came from the point where the callback is being run. So I have added into the PostgreSQL core code for AIO the concept of runtime arguments, such as it is possible to give to a callback when it is run some state, a variable, be it a structure, anything that can be given to the callback based on the state where the callback is being called. But you can also do that with a thing called a conditional state, which is a new, it's a different macro that you can check if the point is being attached, and you can also force a state to happen. That thing was something we did before having the runtime arguments, but you can also do both of them. So you can have a bit more invasive code in your extension code based on injection points to check if I have a point attached, I want to reset this variable, and I can then run a callback. Or you can just set a state and do nothing else. I mean, you can do quite a few things based on that. It's really that it's hidden behind the C flags themselves. But that's kind of to show what you can do in terms of variable manipulation, depending on if callback is set for a given injection point. But you can also give directly things coming from the code path where an injection point is going to be run, and give it directly to your callback to have, I don't know, if you want to take some custom action depending on what the injection point is being given or anything. You can look at the AIO code like test_AIO, which has one example of using a runtime argument inside an injection point. So a small graph, injection point versus time. The concept has been introduced in PostgreSQL 17 in February 2024. And this is a git grep done in the code tree itself, just to show that the number of injection points has been increasing in the tree over time. So this is, I think, something that people will continue to rely on to implement bug tests for complex bug fixes in terms of race conditions or anything. But I mean, things have been going over time, and there seems to be some kind of adoption of the facility among the committers or even people who submit code. But okay, so I'm moving on a little bit with the test facilities. I did mention previously that it's possible to load a callback based on a library. We do have a kind of generic library where that has a set of kind of generic callbacks that you can rely on directly in core. Most of the tests rely on that. You do not have to do it. You could, for example, have your own library in your own extension that defines its own set of callbacks. And you can load your own callback depending on what your own extension has. It's about the flexibility of the facility. Thing is that we also have some basic facility in the core code itself to be able to take some simple actions. Most of the tests in the PostgreSQL tree currently use this module and the basic callbacks we have in that. So this test module is not in country because I wanted to get some flexibility maintaining it, and I didn't want to have any kind of documentation or version or anything that needs to be enforced when we do bug fixing. It's really about being flexible about things and minimize the amount of work you need to do in terms, for example, if I need to do a new bug fix and I need a new callback, I want to be able to define it and not have to maintain anything. I want people to focus on their actual problems, not working around the testing. So they really should do the minimum amount of work in terms of testing, perhaps rely on that as much as they can, but it's really to try to work on the actual deal. So we have a few SQL functions like that are able to also provide testing for the basic infrastructure. You can attach or detach a point. We have a few tests that relies on those SQL functions to be able to attach points, for example. And we have also things where it is possible to wait at a given point and then wake up that depending on the timely manner, such as you can use that for race conditions, depending on what kind of test you actually want to do. You can also run a given point, load. This is mostly useful when it comes to testing. I mean, this was useful for having regression tests in the basic facility. And we have 3 callbacks in this module, which is it's possible to run an error, it's able to issue a notice, and it's possible to use it to wait in a given point. So the callback wait is useful with the wake up one, such as you can use the in-core wait callback to wait at a given place, then use the SQL function to make the process move on. Such as, this is quite useful for race conditions, such as if you have a very tiny window for a given problem, you could just make a given process stop and make it wake up and continue its actions once you've done some concurrent action that allow your original problem to be reproduced. So we have quite a few test cases that actually rely on the wait and wake up logic that we have in this core module. So in terms of the extension itself, it's not everything, but those are the main ones. It's an extension you can use. You can also use those SQL functions in your own tests. One thing that we have is set local, which is quite useful if you have tests that uses an SQL script, such as it's possible to make an injection point only running in the process where this function is getting called. That's something that's been also associated to the private area I mentioned previously, because it's possible to pass down runtime conditions and make sure that you have some variable state that was attached to that was defined when the point was actually attached. So we have a few functions you can rely on if you want. Yes, so local points. This relies on the private area that's associated to a point where attached. This is useful for SQL tests. What you would do if you do want to make a SQL test based on an injection point safe is that you would call this single function injection point set local coming from the module at the top of your test, and then any injection point that gets attached. One important thing is that if you attach an injection point, it's going to be system-wide. So all the backends or any process by default would run it, except if you use that. So in terms of concurrency, if you have a dedicated SQL test based on injection points, you should use that, I guess, to make the thing completely isolated from the rest. If you do that, any point attached in the process that considered the point as local will be detached automatically when the process shuts down. This relies in the module on it's the @shmem_exit callback that we have in the PostgreSQL core code. So you can detach automatically a point that has been assigned to be only local to the process where the point was attached. So if you do something like injection point set local at the top of a SQL script, you can attach something like a point name foo or error. If you try to run it, it would issue an error. And once you detach the process, the point would be gone from the shared memory area where the point was actually attached. So in terms of isolation tests, you can use the isolation tester to use that. We have quite a few tests that rely on it. Who has implemented in this room isolation tests based on the isolation tester? Raise your hand. You, I know, yeah. You, I know as well. So it's really the point. This relies on the wait and wake logic that's in the module itself. So you want to be able to define a point somewhere in the code where actually you want to wait, and you can take orderly actions to order the wake up to have a wake up to happen. So that's a simple example where you have a spec based on a single session that does a setup of a point, and I want this point to wait. So you are attaching a point to wait, and then when you execute the step, you have a wait one step, which will be, when you start a permutation, when you do an isolation test, you will be able to execute the thing to wait. So you can do that, wait, wake up. We have quite a few tests that Noah has written where we've been doing some crazy race condition checks based on that. But that's just to give you an idea about what you can do. We have this spec in the core tree, in the injection points module itself, such as if you do have your own extension and you want to do concurrency tests, you could use that as a base model for your own thing if you want. One thing which is very, very important to know, and something that I didn't, is that if you want to make the wait and wake up order forced, you may want to use what I'm calling here an empty step, such as to make sure that the wake up and the detach happen in an orderly manner. If you do not do that on very, very slow machines, it's possible that the wake up and the result called by the wake up is written after you actually do the detached. So your output may be unstable. It's one of those tricks. So this really also, we have a template in the injection points module itself. So if you have tests, you may want to, you can look at that if you want. In terms of tap tests, like I'm hearing a lot of bad things about Perl. So Perl is what it is. Thing is that we rely on that heavily in the PostgreSQL code currently. And we have facilities where it is possible to define, to do advanced testing using injection points and Perl. So we have APIs. For example, we have a wait for events, which is quite important because most of the logic in those cases is where you want to test race conditions in isolated matters. For example, the checkpointer, and you cannot do that in a live system. So TAP is pretty good at that. The thing is that you want to wait to wake processes in orderly manners, and you want actually to make sure that a point in the code, if you are waiting for a point in the code, you want to make sure that you are actually waiting for it or not. So we have APIs for that in the Perl code. For example, we have a wait for event. You would wait for the event to actually be reached. The event related to the injection point wait you have, depending on the point name you have defined in your code. We have also an object called a background PSQL, which is a PSQL session that remains live, and you can rely on that to make an injection point getting run, and then run for an extra event to happen asynchronously. So for example, if you do that, you have a PSQL background thing, you run a query, you could do some actions, then wait for the wait to actually happen inside the PSQL session you have in the Perl script, and take actions to be able to trigger the race condition you actually want to test in your script. In your script for the problem you are trying to solve. So we do have tests in the core code that do stuff like that. If you work on a bug for PostgreSQL, if you work on a bug on your own extension, you can use those APIs outside of core. So as long as it's in the backend itself. So as the last part of the presentations, I wanted to outline a few examples we have currently in the core code. It's not only that, we have much more than that, but these are simple enough, such as you can get an idea of how we've been using injection points, for example. So one of them was SQL tests related to reindex. We had a bug that has been fixed in this commit, which is from 2024 something, I think, where in reindex, when we do a reindex concurrently, for example, we have wait phases. And we want to make sure that we wait for past snapshots to finish before doing the steps in the reindex concurrently in terms of building things, because reindex concurrently takes a light lock on the parent relation, and we have reads and writes happening at the same time. Thing is that we have introduced, I think it was in 15, the concept of a safe or not safe reindex logic. The issue was that if an index definition has expression or predicates, we wanted to always force the weights to happen in some cases, just to keep it simple. But the problem in this case is that even if an index had expressions or predicates, we would never wait. The issue was that if you had an index definition that, for example, depending on a function that did accesses to another table than the one on which the index is based on, you could finish with corrupted indexes. So when looking at this bug, I was looking at that and say, oh, I want to be able to check easily the state of if an index is actually safe or not, which is basically just knowing if it has expressions or predicates. And that has been finished by being part of a bug fix, because why not? Because it was simple enough to show it, at least in this presentation. So what we have in the PostgreSQL core code is hidden behind the use injection points C flags, 2 injection points that are called with 2 names called reindex conc index safe and reindex conc index not safe, based on a Boolean variable. If the Boolean variable is set on or off, we would take a different path and a different callback. Based on that, I've added, because I did commit this one, a simple SQL test that I can show you today, where it's possible to attach points to those 2 names we have here. And the callbacks called in this case are simple notice messages. So the notice message in this case is that if you do a reindex index concurrently based on a simple index simple, the first one here, does not have any expressions or predicates. And you would see that the notice message is being triggered for this first one. Reindex index concurrently with an index expression would trigger this other notice. So that was just to use that as a cheap way to check if an index was marked as safe or not in the scope of the bug fix. Thing is that, well, this is kind of just to check that the state of the stack is what you expect. And this can work as a simple example as well. So I think the test is actually in the module injection points, if I remember correctly. It would be a SQL test. This relies on local points, meaning that the 2 points attached are automatically detached when you exit the session that runs those SQL sequences. Something extremely crazy that Noah, Mish, Noah, you are not here. I mean, so you can look at this commit. You can look at this SQL test. I've been looking at this, it's an isolation test, actually. You can look at the spec of this isolation test. I've spent hours trying to understand it. I still do not understand it. Point is that Noah has found, I think, through Noah is working at Google, and I think he has found this stuff with some customers. We had an issue, a race condition in the PostgreSQL code base when you try to use some set of ground commands with vacuum and the statistics of a vacuum being updated at the end of, so it's the statistics of a relation updated at the end of the vacuum. So we had a small window where it was possible to corrupt some states of the PG class entries when you updated the statistics of a relation at the end of a vacuum. I don't remember exactly all the patterns that and the original problem that this tested, but point is that we had a very small race condition, and Noah has been using injection points to test all the various patterns he could think of. I don't know how many permutations the test has, but I think it may have 10 to 20 permutations. But point is, if you begin to do that without injection points, you will need, I think, 2 or 3 terminals with 2 or 3 debugger sessions, take breakpoints at very individual paces, but running the test is like taking, I don't know, 2 or 3 seconds. This is really coming down back to the quote of Noah. First is that if you do not actually enable injection points, you would not be able to test any of the scenarios and any of the regressions that we have. Because what Noah has been doing here it's actually Noah who has worked on the part of injection points and the isolation test support. This has been done for his cases, so he has been able to work on the infrastructure based on the basic thing I have added in the tree itself. So you can look at this commit, you can look at the test, and you can see the amount of craziness you can try to do using injection points in terms of race condition tests. I'm pretty sure that we will have many more problems in the PostgreSQL code, but the thing is that at least now we can make sure that anything we fix will not be broken again, because we have the facility to make sure that the tests, and at least we have coverage for that. We did not up to now, so still, we've been okay, but this is, I think, a little bit better. Yes, so that's what a spec, one of the spec that Noah has been using. So that's part of the result of what Noah has committed, for example. So we have, I think the test has been relying on one single injection point where we do a wait. And that's inside the heap in-place update code. So the injection point waits just before we do the in-place updates. And we have other commands that trigger this wait to happen. In this case, it's the vacuum. So you issue a vacuum and you would wait before you do the heap in-place updates of the statistics of a relation. And while you wait, you trigger more things. In this case, it was a set of grant or revoke commands depending on the various objects. So there were patterns related to a table, database. Point is that you can really order things and make various patterns about the race conditions you wanted to test. So these are only the definition of the steps, but we have also on top of that permutations that trigger those steps to happen in an orderly manner. So you can automate what you would do in a debugger directly using an isolation tester. This is much more scalable than what I did for many, many years using Postgres when it came to reproduce issues. In terms of tap tests and Perl tests, we have, wait a minute. So the original bug fix has been fixed here. We have a test that has been committed later on, and that's also one of the reasons why I've been doing injection points. We had a race condition in the PostgreSQL core code between the end of recovery when a node is getting promoted. And for example, if you were at the end of recovery and the node is getting promoted and in the wrong window, the node was getting restarted, you restarted the node and you finish with a famous panic could not locate checkpoint record. So there has been a bug fix for that, but we did not have a test case. The original thread where the bug has been discussed had a test case. Point is that we wanted the restart point, so you required for the sake of the test to have a restart point to run at the same time, because the restart point was actually doing a truncation of some while segments that it should not have been doing. But point is that the test we had that we used to check the actual bug was taking, if I remember correctly, it was, yes, it was a couple of minutes because you wanted the restart point to be long enough to trigger the actual issue. I have added tests that can work as a basic, to give a basic idea of how to use injection points with wait and waits. And this takes a few seconds to be able to run. So we have test coverage based on the facility that has been added. If you want to use injection points to reproduce a race condition, that can be a good starting point to show what you can actually do. We have much more tests that rely on that. So that's, for example, how tap test would look like. We have inside create restart point an injection point where we issue a checkpoint. Oh yes, and we attach before doing any kind of checkpoints a wait, such as we will wait inside the restart point. It's at the beginning of the restart point, but we trigger that automatically. So we attach the point, we have the checkpoint based on the PSQL session, we wait for it to happen. At this point, we know that the checkpointer is waiting for the create restart point. We trigger a promotion, we do a bit more action, but the point is that after waking up, you restart the node once, and if you revert the commit I mentioned before, you would see that the test is actually failing and we have a panic happening. The panic does not happen, the bug is fixed. Another thing that I've seen which was kind of interesting is it's possible to use injection points to bypass states in the backend code. Something that has been kind of annoying when it comes to writing tests that require some strict WAL data, for example, is a concept that we have in PostgreSQL called the standby snapshots. Standby snapshots are used as WAL records generated on the primary and used by the standby to be able to accelerate the state, the list of the transactions we use for the standby state. These happen randomly. And these have been very annoying in terms of the stability of some tests where we expect WAL records to be generated in an orderly fashion. This idea is something I did not even consider was something we should do, but I saw that and say, oh, that's actually kind of pretty cool because you can use an injection point, attach it, check that it's actually attached, and you can skip states or force states to not happen in the backend. The issue that has been fixed here was a stability test issue for the standby logical decoding code that was causing spurious failures in the CI and in the build farm itself. I think we had that, I don't know, oh, you're here. So we had the instability for like, Bertrand is the one, raise your hand, please. So Bertrand has been working on that originally, then also you have worked on that instability, right? With some people from Fujitsu like HOSIGM. And they've been using that to say, I don't want those pesky random records to happen, and they have been using that to stabilize the test as well, which was kind of an interesting use case based on injection points. So they do not call a callback, they just attach a callback with any, you just attach a callback to a point, you just make sure that it's attached and you skip a state. There have been a few things, but the facility I have currently in the core code is kind of at the state where I think it's useful enough for most people to use it. One thing that I've noticed, like it was 2 weeks ago while working on different bug fix, is that it has been a little bit of an issue that the points do not persist across restarts. I have fixed one bug in the PostgreSQL core code that happened at a very early startup of the checkpointer itself. And the only way to actually make a reproducible test was to flush the state of an injection point, restart PostgreSQL, and make the the checkpointer wait early. So I have sent a patch for that. The bug fix has been pushed and backpatched already, but the test was not possible. So I have been working on a solution to basically flush attached injection points that would be reloaded early when you start the server, such as it's possible to have a test based on that. So it's to have a kind of persistence across restarts of the points. Another thing that I wanted to mention to the committee is if at some point it would make sense to actually backpatch the facilities we do have, because I would like people to rely on all that, and it may be a good idea to have regression tests for complicated race conditions and actually make sure that these are fixed in all the branches we still need to support. So we have most of the facility described on this presentation on 17. It's much more complete and I think in the correct state in 18. Point is that should we backpatch it or not? Conclusion, if people are okay with that, I could actually send patches to do it. I'm not asking anybody to do it. I'm okay to do it because I would like people to expand testing and make sure that any bug fix we have actually gets coverage. And bonus points, people would be able to reuse this facility for their own extension work across all the versions of PostgreSQL that are still supported by the community. So I think this is everything I have. If you have any questions.